All right, so if you remember in previous classes we talked about motion sensor and light sensor. That being when there is motion and there is not light, then you turn on this lamp. Now we could have done this with a microprocessor, whereas the microprocessor will take a look at these two I/O ports, and there will be an output port associated with all of the code associated with that in there. And I think you've had C before, right? So we can actually have the input and the output ports represented by ports. I should actually do this in my engineering 1202 course, right? But we're not going to do it now. We're just going to go on. So we're going to look at Boolean equations and then how that would be represented by logic gates. Now, as you see this equation, this is kind of complex, right? You got a lot of parentheses, and we got to take care of C and do the not on that, and then we're going to OR it with B, and then we're going to not that, and then we're going to AND it with A. So let's just look to see what would happen here. We have our final output of F is going to rely on first taking A and ANDing it with a whole bunch of other stuff. But this other stuff is going to start with the not. Then we are going to worry about this OR gate here, and the input for the OR gate is either B, or is going to be B and not C. So now we have the full implementation, C not B, or not C, B, OR together, nodding that, taking A, and then identifying what the function is. So just for grins, just so that we could remember, go ahead and do a truth table for this. Turn to your neighbor, doing a truth table on this with the inputs of A, B, and C, telling me what C or what F is, and you're going to need to do some intermediate ORs and not, or ORs and ANDs, just to make sure you did it all right. So let's go ahead and do that. So pause. All right, so let's take a look. This is what I have so far. I did one, but unfortunately I forgot to do the not once I computed that, right? So notice what I did. I kind of put a little bar over the C. That's another way of identifying a not. And we're going to see that in a lot more detail when we get it more into Boolean algebra. So would you agree that the first step, that not C or B, so we're only looking at this. So anytime we have, first of all, anytime we have 1 in there, we know that it's going to be a 1. So we could always put the 1s right there. And then what we need to do is we need to take a look at when C is 0, that means that'll be a 1, right? C is 0, is going to be a 1. But now we need to take not of all that. So it's 0, 1, 0, 0, 0, 1, 0, 0. Remember, now we've completed this. Would you agree? So again, this is associated with this column. And this is associated with this column. And so now all we have to do is AND A and this column. And of course, since A up here is all zeros, we know that's immediately going to be 0. So now we need to look down here, and oh my gosh, there's only one situation where we have a 1 in F. Ooh, lots of murmuring. That means people are kind of saying, ooh. All right, so have you followed this? Yes? How many people did not get this? All right. Did I do something wrong or did you do something wrong? Okay, just want to make sure. Because it's been a long day. In fact, I saw several of you this morning at 8 o'clock, didn't I? Some of you have 1202, engineering 1202, as well as this class, 2181. So, yeah, I was at 1202 this morning. All right, we got that? Happy? Question? Woo woo. All right. More examples. So here we have an AND gate, and then the next step is we have to worry about this S and D and ORing that together. But interesting enough, oh, and here's another one. Oh man, look at all this. So we have the OR gate all the way at the end, and then at another level we're going to have this AND right here with A and not B, and then we're going to have a B and not C. And look at this little trick here. Since we kind of usually only have inputs on one side, there's A, B, and C. And since B is used here, and we kind of bring it in this gate as well, because first it's used here as the NOT. Goes into this AND gate. So, would you agree this is representing? Now you can start from the output and work back towards the input, or start with the input and work back towards the output. People do it both ways. I'd start with the output. Now, we do have the capability, we manufacture parts that have multiple inputs. So in this case, notice that this A and B and C really could be a 3-input AND gate rather than a 2-input AND gate. Now you could do this as well if you had A or B or C. It would be the same thing. You would have a 3-input OR gate. But if you're mixing ANDs and ORs, no, you can't do that. So let's take a look at another example. We have a seatbelt warning system, and it used to be that I had the exact same car that he had, but I got rid of the car because it was a gas guzzler. So we have here that our seatbelt warning system will be on when the seatbelt is not fastened and the key is inserted. And so we will have a simple equation which we can capture in the Boolean equation, and then we can do the circuit itself. Now here's another skill that you might want to look at is you can actually say, what if I were to wiggle the K and the S inputs? So in other words, I would have K and S as my inputs and I would look at those. And at the same time, I would look at what W is. And so then we would have a timing diagram that would show, here is my inputs for K. So this is all the situations. Take a look at this. This is where K is 0, S is 0. K is 1, S is 0. Then S is 1 and K is 0. And then both K and S are 1. So look at this. We have all of, if we have two inputs, right? This is all the combinations. 0, 0, 0, 1, 1, 0, 1, 1. What we would see for the outputs is, well, let's see. This AND, since this is an AND gate at the end, of these four combinations, how many will result in a 1 for the output? It's an AND gate, right? 1, correct? We have only one situation when we have the input for the AND gate, when this is 1 and this is 1. That will be the only situation when we will see a 1 out here on W. So if we work back a little bit further, here's an AND gate, right? Or I'm sorry, a NOT gate. So then when K is 1 and S is 0 is the only situation where we'll see W as a 1. So I predict that W will be 1 when S is 0 and K is 1. So I'll just wing it, right? And then everything else, I say we're going to have it down here. Oops. We'll make this cleaner. So I believe that this is going to be 0, this is going to be 1, this is going to be 0, and this is going to be 0. Do you agree with me? So, what do you know? It's what showed up. So the whole idea is, you know, an AND gate at the end, that represents our 1 in the situation when you're not fastening the seat belt and the key is inserted. And I think it's more than just the key inserted. I think it's the key inserted and turned. Now we talked about gates versus switches. So, you know, we did this nice logic gates right here, and the representation of this with respect to our actual gate. This would be the down and detailed CMOS implementation. And which one would you rather design in class? Would you rather do this or this? The right one? Oh, here's another question. Or would you rather do this one? Yeah. I think, you know, it's a lot easier to type those characters than to go in and actually drop and click different things and hook them up. So maybe this is going to be an easier way. So this would be almost equivalent to what you would see in VHDL. And you're going to see that coming up not only in this part of the class, but also in recitation. Another example. So now we're going to say, that was simple, right? Seatbelt, key turned. But now we have to make sure that there's a butt in a seat before you actually, you know, say that the seatbelt is not on. Well, that kind of makes sense, doesn't it? Because you're going to want this to work for the passenger as well as the driver, and you don't want this thing screaming that the passenger seatbelt is not connected when there's nobody in there. And you notice that they kind of do that, right? Like the other day, my wife was not. I was driving my wife's car, and she wasn't hooking up her seatbelt because we were going from, you know, one store on one side of the shopping center to another store on the other side, and so she didn't do it. And you know how people are driving at like 80 miles an hour and shopping like parking lots, shopping lot parking lots. That's it. You know what I meant. All right. So again, only illuminate the warning light if the person in the seat and the seatbelt not fastened and the key inserted. So we'll look at that formula, and that's now it's 3 AND gates, right? Or three things that we're ANDing together, and we could do that with that 3 input AND gate. All we have to do is add an additional input. And oh yeah, we're going to also say that we'll only do this 5 seconds after the car is inserted and, you know, kind of started. Because you want to give somebody at least a little bit of time to click it in after you've put the key in, right? Might be 5 seconds, might be 10 seconds. So now you have a little bit of things, and you're going to say, and the you're going to check for T, right? T equals 1 for 5 seconds after the key inserted, all right? Is that right? Should it be or? Well, we'll go with him on this one. So what it's doing is it's going to say, yeah, when this is 1, by the way, T is going to be, let's see, for 5 seconds. Oh, so it's just going to, so what it's going to do is it's just going to say fasten the seat belt for the first 5 seconds, whether or not you have it belted up, so it's a little bit different, right? So your t is going to be 1 for 0 to 5 seconds, whether or not you have the seatbelt in. Do you understand that now? So I was a little bit off on that. So yeah, this would be the logic for that. So now let's look at some gate circuit drawing conventions. All right. So what we don't want you to do is to put X and Y and F inside of your gate. All right. You just do this. And your X is going to be outside, your Y is going to be outside, and your F is going to be outside. The other thing that you don't need to do is draw arrows, because the assumption is always that this is an output, this right here is an output, and this is an input. Now, I made a little mistake there. I actually drew a NAND gate. There's another type of gate, and I believe I covered this in a in the digital or in the engineering 1202. There's another one which is a not and gate, which we're going to actually look at later in the slides. All right. So in this case, the not and, if this were X and Y, this would be 0 in one case and 1 in all the other cases. We'll see this in a minute. All right. And another convention is it's okay to take the output from something and put it into the input of two other ones. But you can't do this because these are two different inputs that you're setting to one single gate. So that's not how you design circuits. All right, you got those rules down? Easy? All right, let's go on. Now that you understand the gates, let's look at another way of representing our digital logic, and this is by using simple Boolean algebra. And I believe we have alluded to some of this in the past, right? We talked about parentheses and ands and nots and the precedents and how you can make things really complex. So let's revisit this. A and B, A or B, not A, kind of cumbersome. So we use this symbol. It kind of looks like you're multiplying this asterisk. But we actually just put it right next together, AB, right? So this here would be P and not S and K, because we have this this little apostrophe right after the A that says it's a not. Yes, sir?
Can we just use the complement bar?
Now, you could also use the complement bar for A, but you know what? It's really hard to type that in a computer, isn't it? And in fact, you really can't do that unless you kind of fake it and use, one of those German characters that, puts an umlaut or the whatever. No, so what we do is for Boolean algebra, so we could type it in later, we just have the apostrophe here, which we use for not. Now, what if I wanted to say we have P and S and K, but we wanted to say it's not everything associated with all that, right? So we want to say not P and S and K. So it would be not P and S and K. Blah, 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 blah. So how would we represent that little apostrophe there for the not? In that case, you would have to put it in parentheses and then add the apostrophe for that. Reason being is that if you just threw it at the end, it would be the not of K, or K not.
Doesn't that also complement the operation?
Well, that would make it, in fact, that's a good question here. What would be the truth table for this? Well, let's take a look. We can do this just for fun. So if we're saying not P and S and K, which I say is the same thing as PSK apostrophe, right? So we have PSK 0, 0, 0, 0, 0, 1. I should draw these separate lines. 0, 1, 0, 0, 1, 1, because otherwise that looks like an and. Oh, yeah. So now we'll do PSK, and now we'll do PSK not. So P and S and K, really, which line is this? It's only that one, right? Everything else is going to be 0. But the not of that would be everything is 1, except for the last one. And if you made the mistake and you said PS not K, that would be looking at the situation where P and S is 1 and K is 0. So in that case, that would be this is 1 and everything else is 0. Does that make sense? That would be interesting. This is important to know, so make sure you understand that. Happy? Copacetic? Understand? Asleep? Good answer. All right. So, when we talk about Boolean algebra, we don't say times or plus, we say product and sum. All right? So let's take a look at some examples. Oh yeah, and S, when you do this, the apostrophe up there, we just declare that as the complement of S, or if we're really lazy, we say S not. All right, let's go to the next slide. Oop. So there's going to be a very important aspect of precedence. Remember, we're talking about parentheses, and in fact, if we looked at this earlier, parentheses and nots and ands and ors. So anything inside of the parentheses, we evaluate it inside the parenthesis first. And you evaluate it from left to right. So let's take a look at some examples. So A and B or C means that first we do A and B, left to right, then we OR it with C. So let's take a look at what we have. We have first, we only need the situation where A and B is 1. Oh, and we give you the input right here. A, B is 1 and C is 0. So first we do 1 and 1 is 1, and then we OR it with C. In this case, the answer is going to be 1. All right, let's look at this. Oh, and this is the, is this the same thing? Oh yeah, remember I said you don't need to put this, what looks like the multiply sign there. This would be A and B or C. Identical. What about this one? So this is A and not B. So in this case, A is 1, B is 1, but not B is 0. So you would say F is equal to 0. And so let's see. Oh yeah, he says the same thing. Phew, good thing. Last thing I want to do is be wrong, right? And, ooh, we kind of saw this earlier. A and C nodded. So what's A and C? And then you take the complement of that, 1. So I would expect F to be equal to 1. like we say here. Do I get another one? All right. Ooh, this is a little bit more complex. We do precedence, right? So the first thing we do is A and not B. So A is 1, not B is 0. So the answer of this is I'm sorry, that's an or. I said it was an and, it's an or. All right, so A or B, sorry. A or not B, so that's a 1. Then we're going to and it with C, 0. Then we're going to or it with not D. D is 1, not D is 0. So the answer of all this is going to be 0. Let's see. Yeah, he goes through a lot of stuff, but we just did that one by one. Easy enough? Okay. Do we have a question back there, or you helping out? Okay. Notice here I'm talking about a function with the inputs of A, B, and C. So with the inputs of A, B, and C, I'm going to be saying, and my variables are A, B, and C, which will be, of course, binary, 0 or 1 later on. This is going to be the complement of A and B and C. Now, this is where we get a little bit different. Well, okay. Then we also have what's called the sum of products. The sum of products means that we're going to evaluate all of this together. Then we're going to OR it with this together. Then we're going to OR it with this together. Then we're going to OR it with this. So that's a little bit different precedence than what we saw earlier. And so we have 4 product terms. Not A, B, C, A, B, not C, A, B, and C. So the sum of products is going to be written as an OR of these product terms. So this is called a product term. And so this is a sum of products. Even though it's a plus sign, it's really an OR. Yes, sir?
If later we do, can we do like different table and we combine them together? Okay, so
do a different table for each one of these and then combine them together? Yeah, you could do that. But look at this. Excuse me. This is a, in fact, if we do the table, this table's going to have how many lines? In fact, you know what? This is a good thing. Let's do this. That's a good suggestion. Let's look at this. And let's do a table for this sum of products. Just for fun. Go ahead and spend some time with your friends and neighbors, and we'll come back and identify what this is. All right, so if we were to look at this, this is what I came up with. Did everybody here have the same thing? So notice I did each one of these separately. One thing I want to point out is that when I restrict this, look at this. This has, this is very specific. There's 3 inputs, and the 3 inputs have to be this and this and this. That means that there's only going to be one in that column for that particular one. Same with this one, right? But now we have 2 possible inputs, right? So that means it doesn't matter what C is. We're just going to be looking to make sure that A and B are both 1s. So in this case, we have 2 of these 2 of the 8 possibilities will be 1. And then when we look at or we don't look at. My hand hit the off button. Here we go. And if we look at this one, the only constraint is C, and so in this case, 4 of the 8 possibilities will be a 1. And all we have to do is look across, and anytime it shows up as a 1, we have a 1 over here in this column. Now, one thing I also want to point out is, are there any what seem like duplicates here? All right, so what would be a duplicate here? Just think about this. Well, we have one here that says A and B and not C. And then we have another one that says A and B. It doesn't matter what C is. Well, heck, look at this. This can represent that one. So you think about it, that's not even needed, right? That's just extra. And are there any other situations like that? How about the first one? Yeah. Here's a 1. There's only one situation where that is true. And that could be represented by this one all the way at the end. So you don't really need that one at all. And what about these two? Well, you notice this. A and B, C, that's going to be totally different, right? So nothing is represented, there's nothing in here that talks about A and B, and there's nothing over here that talks about C. So look at that. We've kind of minimized this equation to really F, A, B, C is equal to AB plus C, or AB or C. So why did we have to draw a table just to realize that, right? Well, that's why we're going to be studying Boolean algebra. Because in Boolean algebra, you could actually take a look at the formula and using these algebraic properties be able to say, oh, maybe some of these I could kind of combine together. So let's take a look at these properties. So commutative, well, A or B is the same as B or A, right? And, oh, by the way, A and B is the same as B and A. And then there's distributed, and this is the one that's the really powerful one, is A and B or C is the same as A and B or A and C. So this is the way we really like to write it. Now comes this one, is that A or B and C is the same thing as A or B and C or A or C. And this is the way you could write this. I like this. This is tricky. All you have to do is remember these properties, commutative, distributive. I'm trying to remember if Dr. Mandrikar said that we could have, if we agreed that we would or would not have a book in the exam. What did I say already? I said what? I said possibly. Yeah, I got to talk to him to find out what he thinks. The other would be a cheat sheet.
You also said that work in groups.
For the exam? Yeah. You think I'm a drunk that... Never mind, we'll go on. The associative is the same as well, as that if you are putting in parentheses A and B and C, it's the same as A and B and C. Associative A or B together or C is the same as A or B or C. Identity, that if you have A and you're ORing it with A, this is just the same as A, right? Or if you have A and you're ANDing it with 1, that's just the same as A. If you're ORing something and its complement, it will always be 1. If you're ANDing something with its complement, it will always be 0, right? Because remember, with A, you have to have a 1 and a 1. And obviously, if you AND something with its complement, you're not going to have 2 1s. On the other hand, if you're ORing A together, you will have in one case a 0 and in one case a 1. So anytime you OR them together, it will be a 1. And let's look at the use of the properties. Oh, remember that A and B and not C? And how do we know it's equivalent to C or not C and B and A? Well, we're going to be using which property? The answer is commutative, right? Because in commutative, it doesn't matter with this A if we put A first or A second. And just because we have 3 ands in here, or 3 variables that we're ANDing together, it doesn't matter which order you put them. All right, how about this one? Ooh. Wow. So here's one thing to take a look at. Does it matter really what C is? Because in one case, C is, well, it's C, and then it's not C. So it kind of makes sense in your mind, right, that C doesn't play into this. But we have to do the algebra. So how would we assess this? Well, let's see. Let's go over here. And how did we split something up? Let's see. What did we have? We have a B, a C and B, right? You know what? I think I'm just going to show you just so you can get a first look. First, you could look at the distributive, right? So you can pull A and B out of both. Remember, we have this A and B and A and C. It just so happens that in this case, is that. And, so, all right. So we got this. You got that? Distributed? Next, well, the complement property. Here we showed it right here. A or A prime, or A complement of A, is 1. So it's always going to be 1. So now we have A, B, 1. And then we remember up here, the identity, 1 and A means A. So we add identity at the end. Ooh, man. This looks like we're going to need a lot of practice for this one, huh? Let's take a look at this one. So what's the first thing? Well, is there anything over here that looks familiar? That's this right here, right? So that would be distributive. So now we have, in this case, x distributed, or x prime is distributed over here and with z. The next is that we have x or x prime, there it is, x or x prime, whoop, complement. And then the identity of 1 and A, and we're left with nothing more than x or z. Whew, man, there's a lot of work here, so let's do some more practice. Oh, he wants to show examples. All right, well, let's go back to this example. So, can this circuit be simplified? I see one thing here. I have an H and a C prime in both sides, right? So in this case, we're saying an automatic door opener, in other words, for a grocery store. F is when the door is open. So a person is detected. We've set a switch saying we're going to force the hold to stay open. And then we have a key that says we don't ever want it to open, right? This would be like closing time. You don't want it to open. So you want the door open when the switch says keep it on and the key forcing it closed is not closed. And we also want to, in other words, we're going to switch it to hold it open. An example would be like in the springtime, I walk into the Harris Teeter, right? And those automatic doors, they just force them open because it's so lovely outside. They just want people just to walk in and get the air in there too. So they'll just force it to stay open, and of course we don't want the door to be locked. And then the other would be go and open it if the switch forcing it open is hold open, and there's a person detected, and we're not locking it. So, does that make sense what this is doing? Yes? What I want you to do is to turn to your neighbor and figure this out. So let me write this up on the board again, just so that you understand it. And then we'll look at the properties. So what is our formula? F is equal to HC prime or H prime PC prime. All right? So what I want you to do is to turn to your neighbor and using the algebraic properties that I just talked about here, solve this. And we'll come back in a few minutes. So let's take a look at the solution of this. And that being, oh, look at the digital logic. Wow, I'm looking at it. Is this the optimal digital logic? Well, let's take a look. So we have this, right? And by the commutative property, you can write it as such. Well, the whole idea is just to take this C prime and put it at the beginning so you can kind of look at it, right? So now C prime is brought out, and you have H or H prime and P. Then you have, from the second distributed property, you can pull out, remember that H and H prime is 1, right? We have H or P here. So now we're left with this C prime 1 and, that's interesting, 1 and H or P, but we know that 1 and H plus P with the identity 1 is an and then we can represent this, whoops, if you look at it, it's just 2 gates, right? It's just this OR gate, and it's this AND gate, and oh yeah, there's going to be a prime, so there's going to be a NOT gate needed for that. So what did we do? We went from 1, 2, 3, 4, 5 gates down to 1, 2, 3 gates. Yes, sir?
Right, so the question that we had is like, you see the fourth step, you see how the one that says the tricky one, I guess, how exactly is that you divide that?
Now let's go back and look at the distributed property, right?
So you ended up with 3.
So the distributed property says, and they said the second, the tricky one, back. So let's look at the tricky one. A or B and C is the same as A and B or A or C. So let's write this down. In fact, let's look at the, let me write it down on a sheet of paper and we'll take a look at that in a little bit more detail. So this is the step where you're having, you said, a little bit of difficulty. So let's take a look at this. So the thing you have to look for is the equivalent in this, right? So did I do that right?
On the PowerPoint, it's supposed to be or for the tricky one. But it says and.
Oh, did I do this incorrect? Ooh, I'm going to have to look at this one and let me think about this for a little bit. All right, tell you what. Let me cover this first thing on Thursday. I think it might be missing an extra step in there. So let me take a look at that and make it a little bit clearer. All right? All right, that's it. Thank you.